Hello, my colleagues. Today we are going to talk about a protocol that we all use every day, often without even thinking about it: HTTPS. As a DevOps engineer or system administrator, understanding what HTTPS really is, how it works, and what happens during a secure connection is critical knowledge, especially when preparing to interviews or troubleshooting production systems. Before we proceed, if you find this content helpful, please like and subscribe. Your support helps grow our community and signals to YouTube that this channel provides valuable information. I very appreciate your help in sharing knowledge. So, let's start with the basics. HTTPS stands for Hypertransfer Protocol Secure. It's simply HTTP with an added layer of security provided by encryption. In the early days of the internet, HTTP was used to transfer plain text between a browser and a server. This was fine for static web pages, but over time it became a bit strange to send sensitive information like passwords, personal data, or credit card numbers over plain text. Anyone on the same network could intercept and read the data. To solve this, a new secure layer was added. HTTP uses a combination of encryption techniques to keep your connection private. Technically speaking, HTTP uses the TLS Transport Layer Security Protocol, which replaced the old SSL, Secure Socket Layer Protocol. Why many still say SSL? What we really use today is TLS. There are two types of encryption: symmetric and asymmetric. Symmetric encryption means the same key is used to encrypt and decrypt the data. This is fast and efficient, but it only works if both the client and the server already have the same key, which is difficult to arrange securely over the internet. That's where asymmetric encryptions come in. Asymmetric encryption uses a key pair, one public key and one private key. You can encrypt the data with public key, but it can only be decrypted with the matching private key. When you connect to a secure website, the server presents its public key to the browser. The browser then generates a new random key called a session key and encrypts it using the server's public key. Only the server can decrypt this session key because only the server holds the private key. Once that step is complete, both the browser and the server can share the same session key, and from that point forward, they switch to symmetric encryption using that key for speed and performance. This entire process is called the TLS handshake. It's invisible to the user, but very critical for setting up the secure session. Once the handshake is complete, every bit of data exchanged between the browser and the server is encrypted with the session key. You may wonder, why do we switch from asymmetric to symmetric encryption after handshake? The answer is performance and security. Asymmetric encryption is mathematically complex and requires much more CPU power. It's too expensive to use for the entire session. Instead, symmetric encryption is much faster. Also, symmetric keys are short-lived. They are generated per session and discarded afterward. So, even if someone managed to break a session key, it would only expose that one session and not all the traffic with the server. Every HTTPS connection relies on this system, and the security depends on the secrecy of the private key held by the server. The public key can be shared without any restrictions, but the private key must always remain secret. Without it, the server can't decrypt incoming session keys and the connection fails. This is also why need certificates. Certificates are digital documents issued by certificate authorities that confirm the authenticity of server's public key. When your browser connects to a website, it checks the certificate to make sure it's valid, hasn't expired, and is signed by a trusted certificate authority. If something is wrong, such as self-signing certificates, expired certificates, or mismatch between the domain and the certificate, your browser will show a warning. These warnings help protect users from man-in-the-middle attacks or fake websites, for example. You are often responsible for managing these certificates, keeping them updated, and configuring services to use HTTPS correctly. You may need to redirect all HTTP traffic to HTTPS, enforce HTTPS policies at the server level, or maybe enable advanced features like HTTP Strict Transport Security, HSTS. You also need to monitor certificate expiration and ensure automated renewal processes are in place, especially when using services like Let's Encrypt. It's also important to recognize that modern browsers and platforms are making HTTPS a requirement. Many new web APIs are only available over HTTPS. Search engines prioritize secure websites, and users expect to see a padlock icon in their browser. HTTPS is not just about protection anymore. It's about trust, compliance, and performance. In practical, understanding this difference helps in many ways. You might be troubleshooting a failed health check on a load balancer, reviewing TLS versions for compliance, or diagnosis a redirect loop caused by HTTP to HTTPS misconfiguration. You may also be writing automation to manage certificates or ensuring their internal services securely communicate using TLS. In summary, HTTPS is the secure version of HTTP. It encrypts communication between browser and server using TLS. The process starts with symmetric encryption to securely exchange a session key, then switch to symmetric encryption for performance. This ensures that the data is protected for any web-facing infrastructure. HTTPS is now a requirement, not an option. It's essential for protecting users, maintaining trust, and supporting modern features. Thank you for watching, and see you later.